We come to question 8 of the addendum. Question 8 says, according to the principle of equivalence, the principle of equivalence is the central principle of general theory of relativity. So what is it about? A, mass and energy are two forms of the same thing. Is that true? And is that the essence of the principle of equivalence? B, space and time are two forms of the same thing. C, electricity and magnetism are two forms of the same thing. D, observations made in an accelerating reference frame are indistinguishable from those made in a gravitational field. E, all of these, all of the above, right? So let's go through each of these. A says mass and energy are two forms of the same thing. Well, this is probably the most famous equation of all time. E equals mc squared, right? So a lot of people confuse this with the general theory of relativity and perhaps think that this is an outcome of the general theory of relativity. This actually happens to be an addendum that Einstein made to the special theory of relativity. It was roughly proposed around the year 1907. The special theory of relativity came in 1905. The general theory of relativity didn't come until 1915. So it was later than the equation E equals mc squared. So E equals mc squared, although A is correct, it is not related to or comes out of the principle of equivalence. So it is true that mass and energy are equivalent, but it's not a restatement of the principle of equivalence. B, space and time are two forms of the same thing. This is also true. They are equivalent, and it so happens that time can be thought of as the fourth dimension, and this is an outcome of the general theory of relativity, which sees gravitation as basically a warping of space, a warping of space-time. So time becomes a manifestation of dimension. So it becomes the fourth dimension. Well, conclusion was made through a variety of means, having to do with the fact that special theory of relativity showed that time is relative, and also general theory of relativity showed that space is the manifestation of gravity. When we combined all of those, then we concluded that time is a manifestation of space and becomes subsumed under space, right? So it's not directly a restatement of equivalence, even though it was shown that they are equivalent. So the answer is not B. C, electricity and magnetism are two forms of the same thing. This we owe to the explanations of Maxwell and Maxwell's equations of electricity and magnetism. And we saw that electricity and magnetism, when combined, explain the nature of light waves, explain the nature of electromagnetic waves. So this is also not related to the principle of equivalence. The principle of equivalence is primarily stated in D, choice D. Observations made in an accelerating reference frames are indistinguishable from those made in a gravitational field. So in other words, there is no way of one person to know whether they are in a gravitational field or whether they are accelerating. Okay? So to illustrate this, again, Einstein referred to thought experiments. Okay. Inside of an elevator, let's say, or a rocket, and elevator is all of a sudden accelerating. Now let's assume that this rocket or elevator is in outer space, free from the influences of all gravitational fields. So let's assume there's no gravity. And then the person decides to let go of a certain object, let's say a ball. Okay. So as the rocket is accelerating, the person lets go of the rocket. What is going to happen to the ball? And what is going to happen to the person? Well, of course, to the person is going to know that they are accelerating because the force of the bottom of the elevator is going to be exerted on the person, right? So the normal force on the person is going to increase. So, of course, this time they do know they are the one moving, right? What's going to happen to the ball? When they let go of the ball, what's going to happen? The ball will fall with respect to the person in the elevator, the ball will fall to the ground, right? So if we took different frames of this, a split second later, the person is here, and where is the ball? Well, according to a person on Earth, if they are viewing this, they let go of the ball, nothing should happen to the ball because you are in outer space, you are free from the influences of all gravity, right? So as soon as they let go of the ball should stay wherever it is, right? So the ball should be roughly about here sometime later, right? So according to this person, stationary person, the ball is simply where it was when you let go of the ball, right? How about based on the person in the rocket or in the elevator? They look at the ball and the ball went down. And so what do they conclude? Well, there's some kind of gravity, right? So the ball is actually going down as if they were in a gravitational field. As a matter of fact, you could mimic the gravity of Earth, right? Let's say the rocket is accelerating at 9.8 meters per second squared, 9.8 meters per second squared. According to the person in the elevator, the ball will feel like it's accelerating down at 9.8 meters per second squared, right? So a split second after that, the elevator will be over here. The ball will be over here. Okay? So according to the person on Earth, the ball is still where it was when you let go of it. But according to the person in the elevator, the ball went down and hit the bottom. So does the person in the elevator know that they are accelerating? Or is it possible that they think there is some kind of gravitational field that's causing the ball to go down? Well, they don't really know. It could be either. Maybe they're going to think they're on some kind of a planet, and the planet has an acceleration of 9.8 meters per second squared. The ball fell, right? And maybe they think that they are accelerating. There's no way for them to distinguish the effects of the two, from acceleration to gravity, right? How about if they happen to be shooting a beam of light? What's going to happen? Say the person was aiming at a certain target. They shoot the beam of light, and as soon as they shoot the beam of light, the rocket accelerated. What's going to happen? Well, according to, depending on whose reference frames we look from, they have different explanations. The person on Earth says, okay, the target accelerated with the rocket. The beam of light should go in a straight line, right? So if you shoot it this way, the beam of light is going to go in a straight line and hit here. So the person on Earth says the beam of light went in a straight line, and because the rocket accelerated, it fell below the target, right? So by the time that the elevator is in this position, the beam of light goes like this, and the target is here, right? So what does the person in the elevator see? The person in the elevator sees shooting the beam of light, and the beam of light is actually curving, right? So person in the rocket will see the beam of light as making a curved path. You will intersect the path of the beam of light as seen by the person on Earth, right? And so eventually it's going to go like this, and then they will intersect over here. So the person in the elevator will say, the path of the beam of light is similar to the path of a ball that I throw in a gravitational field. It's a projectile motion, right? So that means light waves can actually have a similar path and be affected by gravity just as they are affected by acceleration. So either one, there's no way of the person knowing which one is true, okay? From this, of course, Einstein concluded that a gravitational field should be able to bend the light beam, and then the first time that was proven was in 1919, when we did experiments on the solar eclipse, and we actually did find out that the beam of light was actually bending the light beam. of a star that was behind the sun. As the beam of light was going around the sun, it was bending very, very slightly. So the proof of this came in 1919, and that proved the general theory of relativity and the principle of equivalence. Okay? Thank you.